I'm going to. Yeah, I'm giving the solution.
I have it right here.
Let's show that the curve with x equals sine, y equals cosine, that's it? X equals sine, y equals cosine, z equals sine squared. And we're given that this is the intersection of z equals x squared. X squared plus y squared equals 1. Okay, so the first part is not that bad. Basically, you just plug them in, right? So you realize that if you plug in x here and plug in y here, you actually get 1, so that checks out. And obviously, if x is sine, then sine squared is x squared, so that checks out. The second part is probably the problem where it says use this fact to actually sketch the curve. Right, so that's probably where you have trouble. Right, so what does this guy look like?
Circle.
Cylinder.
Cylinder.
Right? So there's a cylinder like running along the z, right? Now this guy, he looks like z equals x squared. So he's going to be cutting through this.
Yeah, I believe that.
Right? So the thing that this tells you, z equals sine squared, that is telling you that the z values range between 0 and 1. Moreover, they bounce up and down like sine because it oscillates. So you expect the z value to, it starts at a high value, then goes to a low value, then goes back to a high value, then comes back to a low value, then continues to come up.
Yeah,
You see it?
what-
So there's like a waviness to the z values, bouncing up and down between 0 and 1 while going around the circle of this cylinder.
What if
And that's
our
going to be-
drawing skills are limited?
Come again?
But what if our drawing skills are limited?
What is unlimited?
Our drawing skills, like we suck at drawing.
Well, vector curves you're not going to be drawing
Okay.
a lot of, so that would be fine. But the things that are important for you to draw are like surfaces, so like
Okay.
cones and things like that, and yeah, that'll be fine. But yeah, that will be it. So it just looks like a saddle inside this thing.
Yeah.
Right?
Will we ever need to calculate saddle points in this class?
No.
Okay.
Relative max and mins, you don't need to calculate.
Okay.
Were there any other questions?
For the homework that we originally had, can you do 10.8 number 10, I think?
Right, that was the one with
The
reparameterizing
yeah,
in terms of arc length.
My question is more of, do we have to be able to use double angle theorem a lot, or use it at all in class?
Yes.
Double angle theorem, we have to use
All
it.
your trig functions,
All right.
everything that has to do with integration, differentiation, trig identities, yes, you have to know all that.
Okay.
It will show up a lot, yes. That kind of question in particular, like reparameterizing in terms of arc length, that's, you're never going to see that. That was just for fun.
For fun.
Yeah. Any other questions? Yeah. That was it.
We're supposed to draw
Yeah.
it, or?
So the first part is to plug these in and show that it checks out. So this checks, and this checks. And then the second part is to actually draw the curve, which you should have some semblance of a saddle or a curve just running around the cylinder while bouncing up and down at the same time. Any other questions? Well, I guess most of the homework was just like a formula plug and chug and then integrating, I guess. There shouldn't be a lot of questions. Yeah, so I guess we will move on then. We're going to move on to 13.2, but let me just introduce the topic. You don't really have to write this down, but I guess for illustration purposes, when I'm explaining, so. You remember back when you were talking about integrals, right? And we talked about integrating along the x-axis between 2 points A and B. And we defined that to be this guy, right? And you could also do the same thing between 2 points on the y-axis, between C and D, and you can actually compute this guy. All right? So you did that, and so this, when you said you're integrating this dx, remember, it means with respect to x, which means your input values are coming from the x-axis. Okay? And if you see an integral like this with dy at the end, it means your input values are coming from the y-axis. Right? So you integrate over some interval on the x-axis, or you can integrate over some interval on the y-axis. Now, the question might have occurred to you, why do I always have to integrate over the x-axis or the y-axis? Right? Why can't I integrate over something else? A random curve, right? So you tell me, I put some random curve in the 2 space, and I say, can I integrate on that curve? The answer is yes. And so the concept of the integral can be generalized to any random curve. You don't have to always integrate on an axis. You can integrate on any curve that you can parametrize, anything you know the equation of. You can actually put an integral on it. And that is the concept of the line integral.
The curve doesn't need to be straight?
Huh?
The curve does not need
The curve
to be
doesn't
straight?
need to be straight. Once you can actually parametrize it, you can have a formula for your curve. You can integrate on that curve. So I can integrate from A to B, some starting point to some end point on this curve, right? So that's the idea behind a line integral. It's a really general form of the integral.
Question?
Yes.
So the difference between this and what we learned about arc length before would be that you can do this for any curve, but arc length is specific for the scenarios you had before, or?
No, arc length also works for any curve. Arc length is a formula, right? You're given a random curve and you want to find the distance between 2 points. You just apply the formula to that curve.
So how does the line integral differ exactly?
Come again?
Like what number, like what quantity is giving us the line integral?
Ah, that's a good question, which I was going to answer later on. I'll get back to that. Okay.
So why do we need
we're
this?
gonna-
Why we need this? Why do we need this?
Oh, it's going to be very important in applications. For example, if for those of you who are in engineering, if you take electromagnetics, you're going to be using this all the time.
Ah.
It's, as with physics applications and engineering applications, it's going to be really important. And I will be doing a few applications later on. But basically, that's the idea. So we know how to integrate over intervals. Now I'm going to teach you how to integrate over any arbitrary curve you feel like. Right? So that leads us to the concept of the line integral. So basically, this involves integrating Let's start with the definition. Right? So remember we defined what smooth curves were last time. These are curves where the derivative never vanishes. It's never zero, so you don't have any sharp corners or jagged edges.
It's not possible.
It's
on
really a nice curve. That's where this definition is coming
So
from.
it's not possible on a on a rigid curve.
Not unless you break it up. So if it can be broken up, then you can use it, which we'll get to situations like that as well. All right? So let's say you have some curve that I call C, and it can be parameterized by this vector function, right? I can actually give you a formula for this curve on some t interval, right? Then the line integral Okay. So this is actually the formula for the line integral. Okay. And notice that we're integrating with respect to arc length. I'm going to teach you how to integrate with respect to x and y later on. But this is basically the definition of the line integral of with respect to arc length. And it's basically going to be you're integrating the function with the parameters plugged in times the ds integral. Remember, we know that arc length was the magnitude of the derivative. That's where this comes
Is
from.
there no limit on the first one?
No, it says along C. This is just notation.
Curve, yeah.
This means you're doing it, you're integrating over this curve, right? And you make that explicit by doing the limits on the parameter and plugging in. Right? So this is just notation here, right? So if you see this, it means compute the line integral over the curve C with respect to R, right?
But doing it to the final C is basically.
Yes, C will be given by block. Or I would describe what C is, and you have to figure out the block. Right? So if I say C is a circle, you should know, you should be able to find this in terms of sine and
Yeah.
cosine. Right? That's why I had to teach you how to parameterize things before. Right? So C, you'll usually be given it, or you'll be able to figure it out, and this is what it means to take the line integral over that curve. Right? As for the physical interpretation, we'll get to that in a second, but this is the definition. This is how you do it. Right? So, yeah, that's that.
That's dot product, right?
This is a scalar function.
Oh, yeah.
They're not vector function. It's a regular product. Okay. And of course, you guys remember what this means, right? It's the radical of x prime squared plus y, right? And of course, pretty much everything I say in 2 dimensions will generalize to 3 dimensions. So if I was asking you to integrate over a 3-dimensional curve, then you just expand this with a z of t and blah, 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 right? But that is the definition of a line integral. So this will actually be an integral on this curve, not on the x-axis, not on the y-axis, but on this curve called C. Right? So let's actually do an example. So a problem you might be given might look something like that. Right, so I say I want to compute this line integral, and I tell you what C is. C is the line segment from this point to that point. Right? Yes?
Okay, so is it dx or d?
ds. Just force of habit. ds.
Wait, are we gonna do it, or are you gonna do it?
I'm going to do it. I'm waiting for you guys to catch up. So I'll make a comment here. You'll notice that like on your quizzes, I just ask you for definitions and stuff. Like just write down what the formula should look like. It's actually a very important thing because things are going to get really strange. For example, ds, we're going to be doing several types of ds integrals. There's going to be the ds, there's going to be the ds, there's going to be the ds. So really being picky with the formulas you write down, it's going to matter, right? So I'm not just asking you just to be annoying. It's actually really important that you keep in mind that the slightest difference can change everything, right? So pay attention to the definition. Know it exactly, okay? All right. That's just a warning. Okay, so I'm going to do integral of 2x dx. So how do I define C, right? Our theorem says I can do this integral if I know C is given by this vector function. So what's C given by here?
The difference. 2 points.
Parameter.
How?
X of t is equal to 1 plus 2t.
Right, so you start at the initial, figure out what you need to add to get to the final, put a t on, right? Then the y, same thing. You start at the initial, figure out what you have to add to get to the final, put a t on, right? And this goes from t goes from 0 to 1, right? That's how we parameterize line curves. This implies that r prime of t would be 2, 3, which implies that the magnitude of r prime of t would be the radical of 4 plus 9. Right? Therefore, integral along c of 2x ds will be equal to the integral from 0 to 1, right? I'm taking the parameters from the t. 2, I don't put the x here, right? I'm supposed to plug in the parameterization. So instead of x, I'm going to plug in this expression here. This is the x of t. Times the magnitude of the derivative dt.
Wait. 2 times 1 plus 2t. Can you explain that 2 times 1 plus 2t?
Right, it comes from this fact here, right? Here I have f of xy, right? It's a function of x and y, but I have to rewrite it as a function of x of t, y of t. So your parameterization actually gives you the x of t, y of t.
Yeah, but
This formula here is your x of t. This formula here is your y of t. So wherever you see x, you're going to replace with this expression. Wherever you see y, you're going to
so
replace
it's a
with this
function
expression.
of that.
Right. So here, this 2x is your f of xy, right?
Okay.
So you're going to take this function, everywhere you see an x, replace it with this.
Okay.
Everywhere you see a y, replace it with that, right? And you're going to get this expression. Now this is just a regular integral, right? So the difference was just the setup. You set it up to get to this integral, and then calculus 1 takes over, right? So you can do this. It's going to be 2 radical 13 between 0 and 1 plus 2t dt. Ask you guys to do this. This should be 4. Okay? Any questions? Yes?
What about the y of t over there?
There's no need to. It's not there.
There is no y,
Okay.
so I don't worry about it. Right? It's whatever shows up, just replace it with the expression in your parameterization. There was no y there, so I didn't have to worry about it. Okay? So you're given a curve, make sure you can parameterize it. It will be something you can parameterize. It's going to be a straight line, a circle, some other curve. I told you how to parameterize everything.
What
whatever
area
you
look
to
like?
parameterize.
So what will the area look like?
Which is, yeah, what we're going to talk about now. But are there any questions on this so far, the mechanics of it? No? Okay, so, yes,
From 0 to 1.
from my parameterization.
Oh, okay.
I say when you parameterize a line curve, if you use the formula that I gave you, it's always going to be 0 to 1. There are other ways to parameterize line, but that was the standard. I gave you the standard formula for 0 to 1. So now, of course, the question that y'all ask, what does it all mean? What is the concrete interpretation of the line integral? Well, we know what it is in calculus 1, right? When I say the integral from a to b of f of x dx, that gave me the net area under the curve, right? When I do this computation, what it gave me was this area, right? This is equal to the area, right? That's what an integral was about. The integral was a tool developed to study area, right? Same thing with this guy. If I do this integral, it gives me that area. That's what an integral is about. Well, at the end of the day, a line integral is just an integral. So it also gives you an area. The question is, what area does it give you? It gives you the following kind of area. If you expand your vision to 3 space, now your curve in the xy plane is going to be some random curve, right? Something like that. Your f of xy, right? Remember from calculus 3, sometimes they say z is equal to f of xy, right? Just like sometimes when you see f of x, you can think of it as the y value. It's the same thing here. So if you see f of xy, you think of that as the z value. So the height of that function is giving you the z coordinates. In other words, if this is your curve c, then your f of xy is some function above here, some surface hovering over that c, that's going to define the height of this fence that's above this curve.
So it's still kind of like a box shape anyway.
Yeah. But now you form a fence, right? Where the height is given by f of xy.
So no matter what, it'll always be a boxy shape. There's no way that they can find the area of some odd
It's not going to be a box. It depends on what your function looks like. If your function is actually wavy, then this will follow it. Right? The height of your fence at any given point is given by the function.
Yeah,
Right? So at the point x0, y0, what you do is you plug it into the z function, you get this guy, and that's going to be how high you go up. And you do this pretty much for every point going along this curve.
Oh, so here, so that's why it's a box.
Yeah. So here, if you see the integral of f of xy ds, what that means is it's the area of one side of the fence, for lack of a better word. Right? So you have some random curve in your xy plane. The height above that curve is dictated by some other function. If you do the line integral along that curve of that function, it will actually give you the area that spans along this fence.
So we assume that the thickness is nothing then.
The thickness is nothing, it's infinitesimal.
Okay.
Right. But it gives you the area of the side of the fence. That's the concrete interpretation. Now you're never really going to use that interpretation per se, which is why I didn't introduce it before, but that is literally what the number means, right? But you're never going to be asked, oh, compute the area of this fence. It's not going to happen, right? But that's what the interpretation is of the line integral, right? So it's a much more general thing. The area actually extends into 3 dimensions. Let's do another example just to get used to things. Very similar to the previous one, except I changed what my C looks like. Okay, so you guys lead me through. How do we do this one? Yeah?
It's a circle over here too, right?
Right, so you're going to parameterize the C. What is it going to look like?
Well, x equal to sine theta, I mean cosine theta, cosine
Come
theta.
again?
X equal to cosine theta.
X equals 2 cosine.
Cosine theta. Yeah, 2 cosine theta.
Never said 2. Y is equal to 2 sine theta. Right? And what are the limits on my t?
0 to I.
0 to
Right, so let's look at what we have here, right? So what does the picture look like, the curve that we're integrating? Quarter circle, right? So this is a full circle, but I only want a quarter circle. I want to go from 2, 0, which is here, and move to 0, 2, which is here. Right? So this is my circle C.
Number 2.
Right. So this is one of the reasons why being able to draw something is important, right? So if you actually draw a picture all the time, it actually helps you to set this guy up. So you see this is what I described, draw the picture. Then you'll be able, oh, it's going from an angle of this to that. I know how to parameterize a circle. So then this is that. Yes.
Because it's a circle, would it really matter? Couldn't we just take a quarter of a circle, like let's say pi over 2 to pi, and still get the same answer?
Not always. It depends on the function you're doing. In this case, you probably get the same answer, but it's very important that you look at where I'm saying. So you don't just take any part of the curve. You have to take the part of the curve that they're talking about. Right? Things can actually be different. So at one part of your curve, your function could be positive, for example, whereas in some other region, your function is negative. So you don't just randomly pick a region, right? You focus on a particular region. They'll always tell you exactly where they want.
Okay.
Right? So I want the quarter circle, the part of the circle that moves from this point to that point, which is from here to here, and
Wait, so we're assuming that negative area is possible.
yes,
Okay.
negative area is possible, right? The net area. Okay, so R prime is minus 2 sine, 2 cosine. What's the magnitude of R prime?
1,
2.
It's going to be 2. Right? It's going to be the radius of the circle. Therefore, the integral along C of 3x ds is equal to what?
0, 2.
Come again?
16 integral.
Integral, what are the limits?
0.
0 to pi over 2. What are right here?
6 cosine t.
It would be 6 cosine t, right? Because the 3 is there, and I multiply by the x, which is 2 cosine t. Now the ds is replaced by the magnitude of that dt. So I multiply by another 2 dt, right? So that's your 3. This is your x, right? This is your ds, right? So we end up with what?
Integral, that can solve.
What's the integral of cosine?
Sine. Sine.
Positive sine.
Yes.
And what's sine of pi over 2?
Half, I think? No, 1. It's 1.
1. What's sine of 0?
Yeah.
So that's the answer.
Alright, for the 3x part, what would be the difference between that being 3x and that being another function?
The height of your fence. So we're going to see how to interpret line integrals because they're going to give us things like work, which we're going to do later on. But
So we're doing
basically that's
function
it.
work?
This particular interpretation here of the area of one side of the fence, it's not really useful in practical purposes. At least it won't be in our class. Yeah. You should just know the mechanics of it. Okay?
So I expect we'll be doing some problems like that revolve around magnetism where they give some functions and just...
Not in such detail. You might be given problems where I actually compute the work in moving an object or something. Something really,
force time dot
something like that. We'll get to it. Any questions on that? So this is just a final formula. You draw a picture to help you figure out the parameterization and the limits, and then you just plug and chug, basically, right? So here's 392, and then from here, your previous classes take over, right? There will come a point where you'd have to compute double and triple integrals here, which is why I made you guys review that, right? But the only thing we're learning in 392 is the setup is going to be different. Everything else, you're going to have to remember from calculus, calc 1, 2, and 3, right? It's going to be important. Okay, so that's that. Now, to answer your question about the jagged curves thing, this is real life, right? Not everything is always going to be smooth. But pretty much everything can be modeled to be piecewise smooth, and here's what we mean by that. Piecewise smooth. So for example, I'm given a curve that looks like boom, 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 right? Something like that, right? So that's not a piecewise, that's not a smooth curve because it has sharp corners here, right? I cannot integrate or differentiate over sharp corners, which is a problem. But the thing is, if I just cut it up into pieces, each of these curves on their own are smooth, right?
So you add them pretty much.
So, right, you're going to add them together, right? So it's the analogous interpretation to the integral, right? So there are going to be cases where, in a case like this, right, if you're finding the area between these two curves, right? Remember, area is the integral of top curve minus bottom curve. But obviously the top switches here. What you can always do is you can always split the integral into two pieces and find the area by doing this integral plus that integral. In a very similar way, we'd be able to do this. So the idea would be to break this curve up. You can call it C1, C2, C3, C4, right? So you break up the curve C into a finite number of other curves which are smooth, and you're going to apply the theorem to each curve separately. Right? And so if I actually, for the integral along C of f ds, that's just going to give me the integral along C1 plus the integral along C2 plus the integral along C3 plus the integral along C4. Right? And this is very informal notation, of course. I don't want to have to write the f over, right? But basically, that's what you're going to do. So you're going to, given a curve that's piecewise smooth, and you're going to have to break it up into pieces. Each piece is, of course, going to have different parameterizations, different limits. You just, once you break it up, you just go by the formula for each one, and you add them together, and it will be exactly the same as doing the line integral over
Is
the
it
whole
possible that some pieces will be in different forms of the integral? Like some of it will be easier to solve using polar coordinates, and other would be easier to solve?
Yeah. So, I mean, each integral is an integral on its own. Like,
Oh.
anything goes. Right? So that's how you deal with things that are not smooth in general, but that are piecewise smooth, right? And I'll never give you a worse situation than this, right? There's always going to be a situation where you can break it up into things that you can parameterize nicely and integrate over. So let's do an example of that one. So you might be given a question like that, right? So compute this line integral over C. Our curve C consists of a quarter circle going from this point to that point, followed by a straight line segment going from this point to that. First thing you might want to do is draw a picture. So again, quarter circle starts here, ends up here. Right? This is from 1, 0 to 0, 1. And then you have a straight line going from 0, 1 to 0, 2. So it runs along the y-axis and ends up at the point 0, 2. So this is my curve C. Right? So I start here, go along a circle, and then I go along a straight line. This is a sharp corner. The curve is not smooth, but it's piecewise smooth. I can break it up into two parts, the circle and the straight line. I know how to parameterize each of these. Right? So we're going to do the integral along C1 plus the integral along C2. Right? So now let's look at C1. Right? How do you do the first curve? What's your R?
1.
Cosine t.
Cosine t, sine t. What are your limits on the t?
0 to pi r.
0 to the power of 2. So your r prime is just minus sine cosine magnitude of r. Alright, you're going to take the square root of sine squared. Sine squared, which is going to end up being 1, right? And so you would have the integral along C1 of x squared ds is equal to the integral from 0 to pi over 2 of x squared. Our x was cosine, right? So that's cosine squared times the magnitude, which is just 1, dt. Okay. How do you integrate cosine squared?
Cosine squared, you have to use
Substitution.
No, it's
double
angle formula.
Right? 1 over 2 times 1 plus cosine 2t.
I hate that formula. But I feel it.
Got to learn to like it in this class. Okay, so now what? Well, prime integrate, right? Integral of 1?
Wait, well, why do you do that? Why not just make 1 equal cosine squared plus sine squared, and then change?
T.
Well, it's not.
So integral of 1?
Okay.
Integral of cosine 2t?
1/2 sine
2 sine.
1/2 sine 2t. Right? And you're going between 0 and pi over 2. Obviously, you plug in pi over 2 or 0 into this, it dies, so this guy is the only guy that matters, and it's going to be this times. Right? So we have pi over 4. Right? But that's not the whole answer, that's just the answer for C1. Right? Then you're going to have to do the whole process over for C2. Right? Now C2 was what? The straight line segment from 0, 1 to 0, 2. So we're going from 0, 1 to 0, 2. Your R of t looks like what? 0.
1 plus 1, 2.
1 plus t. Right. T goes from 0 to 1. Your R prime of t is just 0.1. Your magnitude then is just 1. So your integral along C2 of x squared ds is just going to be the integral from 0 to 1 of x squared. But what is the x? It's just 0. So it's just 0 squared dt, which is just 0. Therefore, the integral along c of x squared ds is going to be equal to pi over 4 plus 2. Any questions? Yeah.
Can you do perhaps like a visual representation of C2
Straight line.
and why it completely
Oh,
drops
it's
out?
right here. So this would be C1, this would be C2. This is the picture that would be helpful.
So that line has no area.
Come again?
So that line has no area. No, never mind.
There's a before.
And
So
Wait.
the fence would have no height
At that,
once you get to C2.
yeah.
well, remember it's the net area. So it's possible for one part to be positive, the other part to be negative. But in this case, no, it actually has no height, right? Because the height of the fence is given by x squared,
Yeah.
and for this part, my x is actually 0. So
Yeah.
there's actually no fence. So
So what's the point of the line then?
what?
So what's the point of the line then?
Well, what do you mean? What's the point of it?
I mean, if there's no fence there, then what's the point of even including it into the?
Well, you didn't know there was no fence there until you actually did this, right? You have to parametrize it first, and then you'd see this. So it's not always going to be 0. There's no. Sometimes you can get answers for each, and you have to add them together. I just gave you an example where the second one is easy. And I think we'll end there. Next class, yeah. Was there a question? No, this is just a constant. It's gonna die. No, we're not done with the second. So I told you line integrals over arc length. Next class we'll do it with respect to x and y as well.
Are we gonna
No, the homework for this is not.
start fundamental theorem next class too? You think?
No,
And
that will probably be the class afterwards.
and are we gonna have a quiz on Wednesday?
Yeah, there's a quiz. Not this. No.
Not Wednesday,
Like-
but next week, Monday.
Next week.
Alright, cool.